This is the picture that my high school teacher drew for me back home in high school in South Korea. Okay, we have dominoes, domino number 1 through n. And we want to prove that all of these domino pieces will fall. Well, we can wait until this thing falls down, but then this n can stretch out potentially to infinity. Actually, they usually do. So we don't have enough time to wait eternity through eternity. You know what I'm saying? Those of you, you know what this is about. It's induction. You cannot really prove it for all positive integers. You know what I'm saying? There are infinitely many of them. So we have to have a new way of thinking, and that way of thinking is assuming this case, this is domino number k, and k is somewhere between 1 and n. Assuming this case domino will fall, right? And if I use nothing but this one to trigger the next one to fall, does this set off a chain reaction and then everything will fall? For example, if k is equal to 1, then 1 will tip 2 over. You know what I'm saying? Now k is equal to 2, that 2 will trigger 3 to be true. 3 will trigger 4 to be true, and then so on forever. You follow? Is that enough to prove that everything will fall? Feel free to use your microphone.
Yeah.
Do you have to prove the base case?
Yeah, the baseline, the first one. See, somebody has to tip this first one over because this ain't gonna tip itself. Everything else will rely on the previous domino to tip, right? But this, somebody has to do this. So in the playing with dominoes, this is you, right? Ding, and then it sets off a chain reaction. So this is the idea behind induction, okay? Induction, number 1, first case, you have to prove baseline. Meaning, you have to say first case is true. Case, wow, learn to spell. Why did I write cast? Case is true. You have to prove this thing called the baseline. And then number 2, assume, suppose k is true. Case is true. Then you will have to, this is if then you will use that to show that the k plus 1 case is true. This is how you prove induction. And you have done this before, so this is a nice review, okay? Now, let me briefly mention, this is what's known as the weak form of induction. This is like most popular one, and then only thing that's done in high school, okay? But let me give you a strong case of induction, strong form of induction. There's some people do it in college. So like in case when you go to college and your professor does it this way, don't be alarmed. It really is the same thing. Okay, strong form of induction. I'm not going to write it down because this is the only thing we are going to do. But strong form of induction says, number 1, you still have to establish the baseline. And then you, instead of assuming case is true, you assume everything is true from 1 through n minus 1. And then will that trigger the last one to be true? If you think about it, it's really the same logic. Look, if there are only 2 of them, and then this one, up to this one is true, will that trigger 2 to be true? Now, once that is done, then now there are 3 dominoes, and 1 and 2 happened. And then will that cause 3 to happen? And once you've done that, then there are 4 dominoes. You see, this is really the same thing. You can just keep adding the last one forever. You know what I'm saying? So that's known as the strong form of induction, which you don't have to worry about in high school, okay? Because this is the only thing on the test. Now, so I'm going to take another example instead of diving right in, okay? So example, this is like semi-induction. This is not really induction, but example. I'm going to take an example. And my example is this one. Let's say 1 plus 3 plus 5 plus . This is like number 1 in your list, and then 2n minus 1. Do you know what this adds up to? Odd number pattern? This adds up to this. Okay, it's not a formal proof, but this is the idea behind induction. Okay, if n is equal to 1, then on the left-hand side you have this, and on the right-hand side you have this. Equal sign. On the right-hand side you have this, which is true now, isn't it? And then when n is equal to 2, then on the left-hand side you have this, and on the right-hand side you have this, which is still true, isn't it? And then n is equal to 3, and then 1 plus 3 plus 5, and the right-hand side is this. Oh, that's still true. You know what I'm saying? And then usually people notice the pattern and do dot dot dot. And n is equal to, this is a little stupid, but n is equal to n. Then, oh, I did it again. Okay, see, this is what I warned you about. My wrist brace is pressing the sleep button on the. Is there a way to disable the keyboard? God, I wish there's a way. Because this has happened every single period today. Okay, so I'm gonna scroll up and write plus 5 dot 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 plus dot dot dot, and then plus 2n minus 1. And that'll of course be n squared. I mean, this is the idea behind induction. You recognize the pattern and say dot dot dot. But we are going to formalize this. You get it? Okay, so we'll take the real example. Now, go back to black, then we'll say prove this. Summation of I squared. And I will start from 1 to n. And that formula you don't have to memorize. For some reason, I cannot memorize this if my life depends on it. This formula. Okay. Okay, now here's what you have to be very careful. Okay. Do not use sigma notation to prove induction. I mean, it could be done, but chances are you're going to screw up. Even the professors, they rarely use sigma notation for this. Sigma notation is just nice, lazy way. So what we are proving is this. i.e. 1 squared plus 2 squared plus dot 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 plus n squared is equal to n, and then n plus 1, and then 2n plus 1 over 6 is what we want to prove. You know what I'm saying? This is, so use this notation. It's more writing, but you're not going to screw up. You with me? Okay, let us prove. So, and you know that you have to start the proof with proof. You know what I'm saying? Okay, so first, if for k is equal to 1, or n is equal to 1, right? Let's see if baseline is true. On the left-hand side, you have this, right? And on the right-hand side, if you substitute 1, you have 1, and then 1 plus 1, and then 2 times 1 plus 1 over 6. Does that thing simplify to 1? Yeah, it does, right? So this is true. So this is true. So it's true for when n is equal to 1. We have established the baseline. This is the first domino. And then, now we say, oh, I forgot to put the, you don't have to put this number, but I usually do. 1 and 2, subscript. We need Roman numeral 1, and then 2. Okay. Assume or suppose, which sounds more, let's go with suppose. Many professors usually use suppose instead of assume. You can say assume, but suppose. Suppose this is true when n is equal to k. Kind of thing, right? So what we are supposing is this. 1 square plus 2 square plus dot 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 all the way to k square. K is somewhere between 1 and n. Happens to be exactly our formula. K plus 1 and then 2k plus 1 over 6. We are supposing this is true. And you don't have to write this part, but I'm trying to be a little more professional for some k. That is between 1 and n. How about that? Are we good? Now we are assuming this is known as the induction hypothesis. And using nothing but this, can we trigger the next stage to be true? Okay, and writing this is totally optional. Did Miss Slattery made you write this? Need to show? This is what we need to show using nothing but our induction hypothesis. 1 square plus 2 square plus dot dot dot. Here's a k square, but we have one more line, and then this side as if you replace k with a k plus 1. So this becomes k plus 2, and then this becomes 2k plus 3a. Too much algebra? We need to show this is true. Okay, to me this green, what is written in green is optional. You don't have to write it for me, but this is your guiding line. It's mighty convenient to have it anyway, okay? Because you look at this and see where you're going. You with me? Some teachers require this, some teachers don't, okay? Okay, now let's go. And oh, a lot of people say, oh yeah, substitute k plus 1 for k, then it's true. No, 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 that's not how we do it. Then you can prove about anything, right? That is not true. No, that's not how you do it. You have to just use nothing but this and whatever's allowed in algebra. Okay? So let's go back. Oh, one good thing about teaching with computer is I can do copy and paste. I'm gonna do that. So this is what our induction hypothesis is, right? I'm gonna squeeze some room. And then we're going to add something on both sides, which is allowed in algebra, right? And what I'm gonna add is the very next term. Follow? Okay, now the other idiocy that I see a lot is some students are too lazy to write all of this and omit all of this and say this term is equal to all of that. That's definitely not true. Are you kidding? Right? This is calculus BC. Let's not say this is a second degree polynomial. This is one third degree. Are you kidding me? You have to write all of this will add up to this, because we are just taking nothing but our hypothesis and we added k plus 1 squared term on both sides. You get it? Now look, the left hand side already looks like what I want, right? This is where I need to go. So all I have to do is use algebra to tweak this thingy to make it look like that, and then we're done. You get it? Okay, so here we go. This is equal to, do you see the common factor, k plus 1 term? Yeah, let's factor that out. So we have k plus 1, zoom in a little bit, and then common factor, then we'll have k here, 2k plus 1 here over 6 plus k plus 1, 8. Too much algebra? Are we good? This is equal to k plus 1 here, and then common denominator. So we have k. I'm going to multiply this out. So let's multiply this. So we have 2k squared plus k over 6. And then let's find the common denominator, which is 6 here. And then we have 6k plus 6. Still with me? Okay, I'm going to add. So we have k plus 1 here. And this thingy becomes 2k squared plus 7k plus 6 over 6. Still with me? Now my question is, will it factor to this thingy? What do you say? Still remember factoring? K plus 1 here, and then k plus 2, and then 2k plus 3, 8. Wow, it worked. Because that's exactly what we wanted up here, isn't it? You get it? So what we have established is this whole thing is equal to this, which is exactly what we want here. Okay, we need to finish this off, so I'm going to do another copy and paste. Go down here and say, paste it here and change the color. Change the color. Therefore, I can say, therefore, this is true as well, right? Meaning I have just proven it for the k plus 1. Then now we have to finish it up, right? Therefore, it will set off a chain reaction and make this thing true. I'm going to copy and paste this. Oh, not that one, this one. Well, if there's a one good thing that came out of distance learning, this is easier. Oh, that's 6. I'm going to get rid of that 6. Now, so we can say, therefore, this is true for all n. Questions? This is how you prove something with induction. Do you guys follow the logic here? Okay. On the quiz, not this one, but 3, 4, or 5 on the quiz. So you will prepare all 3 of them. And some of them are quite lengthy and ugly. Okay. Alrighty. Then the Riemann sum. How do you do Riemann sum? Okay. So let's do that. So the Riemann sum integral question that goes with this particular induction will be like this. Now we evaluate f as integral 0 through 4 of x squared dx. And then we have done this with a calculator. Wait, did I show you seen the video, right? How to do this with a calculator and you get 21 1/3. You want to see that again? Nay? You've seen it, right? Okay, so this answer we expect it to be 21 1/3. Okay, and then you remember the syntax, calculator, whatever that means, right? Okay, now here I have some graphics for you. This, do you remember the left and right rectangle? See, this area is what we are trying to calculate, and this better turn out to be 21 1/3. This area right there. Okay, and then you can do this with your calculator, actually a lot more accurate than this thingy, but if you use the left rectangle, that was 14. This is like little limitation on this program. And if you use the right rectangle, then it'll be 30. Right, and there's a gap between the two. I mean, humongous gap between this and this. It's kind of like election polling, right? One candidate is leading by 17, and no, the other candidate is leading. Right, these guys need to go out of business. Okay, and then of course mid rectangle is somewhere in the middle, right? That one, 20. What our answer was 21. But then it doesn't matter. We'll just look at the extreme cases, right? If I use 8 rectangles instead of 4, and you can do this with your program. You see that gap between the two has narrowed quite a bit already. And then, of course, yeah, while you're at it, double it. Wow, it's getting closer. You see where this is going, right? Then should we use 100? jump to a big number right away. You see how smooth this rough edges are, and these two are very, very close, but still some gap. Well, 1,000. Add one more zero while we are at it. Our gap is. Do you see this is begging for a limit now? So why don't we use infinitely many rectangles then? The gap between the two will close down to 0. But the limit means it's not equal to 0, but it's infinitely close to 0. You get it? So we're going to do that by hand now. Okay? Okay, let's come back to our notes. So our function that we are integrating will look like this. Let's throw it here about yay big. Okay, and then this thingy will have a shape, let's say, about like that. Right? Okay, now we are to chop this thing down. This is up to 4. This is 4. You get it? Okay, now we are supposed to chop it down and then draw rectangles, right? Okay. I'm gonna draw, I'll just draw vertical lines actually. I take this back. Say, this is about halfway, right? And left and right rectangle does not matter. So, but right rectangle is easier to set up. So you can on the test do it with the right rectangle. It's a lot easier. Trust me on this one. So that one didn't work out. Right, this is. I want to erase. Huh. What is wrong with this thing? I guess there's a minimum. That's great, right? Okay, and I'm gonna actually chop it down a little more. So we'll practice with 8 rectangles. So suppose there are 8 of these things, sub-intervals. Just slightly to the right. That, and I need one more. I know, see, this is a minimum, so it's like, we'll have to live with it. Okay, these are the 8 of them. But I'm gonna I'm gonna concentrate on rectangle number 5. 1, 2, 3, 4, that one, right? So our rectangle number 5 in particular looks like this. 1, 2, 3, 4, 5, that one. Gonna make it red. You know what I mean? That's our rectangle right there. Okay, and then I'm gonna write down 5 inside of it. First, we'll practice with numbers. Okay, let us practice. We have to find the area of each rectangle and add them up, kind of like what you did in homework, rectangle approximation. Okay, so let's just think about this red rectangle. So that I'm going to call it delta A. Delta A number 5. How do we calculate the height of this thing, and how do we calculate the width of it? Okay, so first of all, do you see that this is delta X? You know what I'm saying? The width. So do you see that delta X is equal to 4 over 8, which is 1/2? Do you see it? Okay, and then, okay, I'm gonna erase this thing now. Then I'm gonna call this thing X asterisk, that point, X asterisk. right there, because that's where we calculate the function. You know what I'm saying? This way is the f of x asterisk, isn't it? Good. Okay, so, and then the reason I put asterisk is because it could be right, left, or mid-rectangle, right? Or anywhere in between. How do we calculate x asterisk here? Somebody tell me. X asterisk and x star, they say, in this case, is it 5 times 1/2? Do you believe this is 2.5? Did I draw the rectangle in the wrong place? 1, 2, 3, 4. Oh my God. I drew it in a, well, we'll do it with rectangles. No. Oh my God. Why are you guys watching just in your amusement? I'm gonna move this guy over. Ah. That worked out. See, something about the computer is you can actually erase your sins. Let's see if I can zoom in and erase this thing. No, see, I knew that was going to happen. Precision. Okay. Okay, good. So this is what I'm calling x asterisk right here. And this is rectangle number 5. Do you see at the moment this is 2.5? And then you have to think like a programmer. How are you going to calculate this? Is it rectangle number 5 times the width of each rectangle? You know what I'm saying? So this gives you 2.5. Say you understand this much, because we're going to do this with symbols. And this is what programming is. You practice it with the numbers to come up with the algorithm, then you can teach a computer to do it. Okay, so this thingy, is it, how do you calculate, oh yeah, before we do that, we need to calculate the height of this rectangle, which is a value of the function, isn't it? So is this thingy f of x asterisk is equal to 2.5 squared? You with me? If this is 2.5, this is 2.5. Now I'm going to have to erase that, right? God, that's great. They're amazing. Is this thingy. Good. Okay, so what we have is f of 2.5 squared times the width. So in reality, this is 2.5 squared times 1/2, 0.5. You with me? Are you with me on this one? Okay, now we are going to do all of this without numbers, okay? Okay, I'm gonna shove this thing to the side and we'll do the parallel thingy in blue. So delta x, and this kind of is like, do you remember chapter 12, was it the formula of this thing? You have done this before? That has to be b minus a over n, because this is b, this is a, right? A at the moment is equal to 0 and b is equal to 4. Good. So 4 divided by, at the moment, 8, but we're going to take infinitely many rectangles, so good. Now x asterisk then has to be, this is I, rectangle number I, so I times delta x, which is that thingy. Good. In our case, it happens to be 1/2. So we got 2.5. You with me? And this is just thingy square. So in our case, f of x asterisk should be x asterisk squared. Okay, so delta A, not phi, but ith rectangle. This is a formula that goes inside the sigma notation. Happens to be f of x times delta x. Good. So in our case, it will become x. Oh, I pressed something again, right? Asterisk times b minus a. I'll just write delta x. B minus a over n. You with me? Say yes. Square. I forgot square here. I'll just get rid of this. I'll do it inside the formula. Okay, then. Let's finish this thing off. So this thingy, by definition, is equal to first space sigma I from 1 to n, and then we put that thingy, right, delta A, which is f of x asterisk times delta x. Delta x is not really in line. Do you get what I'm saying so far? Now, and then, as you saw in the graphics, many more rectangles are more beneficial. So infinitely many rectangles. So we are going to take a limit here as n approaching infinity. Okay, this is what they call Riemann sum. It requires that limit right here. Not what rectangle approximation that these textbooks call Riemann sum. Okay, this is what real Riemann sum looks like. And then you're wondering, some of you, why there's a dx here, right? That dx is really infinitely small delta x. Remember the infinitesimal delta x, Leibniz ingenious notation? So that's what that thing is. You with me? Can we evaluate this? Okay, so this is what you have to pull off on the test. So let's go. This is equal to limit of n approaching infinity of I from 1 to n. And f of x asterisk is, of course, in our function, our f of x here happens to be x squared now, isn't it? This thingy inside the integral. So x asterisk squared times delta x. So far so good? Okay, now that is equal to limit of n approaching infinity of sigma I from 1 to n. Now, what is x asterisk? What did we figure out here? Right, I times delta x, eh? So we have I times delta x squared times delta x. Still with me? Okay, that should be equal to limit of n approaching infinity. This is lengthy, sigma I from 1 to n. Sigma notation is the most annoying thing in mathematics now, isn't it? Wow, that is I times, so I squared, delta x squared, delta, you know what I'm saying? Delta x cubed. Good. Because there's a delta x squared and there's another delta x out here. Still with me? Okay. Now that is equal to limit of n approaching infinity of sigma I from 1 to n I squared. What is delta x? This thingy, b minus a over n. Right? In our case, we'll just put 4 over n cubed. How's that? Good? I'll just write here. In our case, this is 4 minus 0 over n. Still with me? Okay. I think I need to clean this up a little bit because I'm not having a whole lot of space here. I'm going to move the whole thing to the right just slightly. I need more room. Okay. This is going to be interfering. Now, whoa, let's just concentrate on this part right here. That look familiar to you? Everything else does not have I in it, it's just n and then limit n, right? But that thingy, why does that look so familiar? Because that's the induction that we just proved, huh? Right here. Oh, so plug that in now, right? For the sigma I square now, isn't it? Yeah, let's do that. So what we have now left is equal to limit of n approaching infinity of, oh, I wish I can remember the formula. What is it? N plus 1, 2n minus 1, right? Over 6. And then we have 4q. What's 4q? 64, is it? Over n q. Oh, I'm gonna make this thing red so you can see where that thing came from. So far with me? Okay, one of the n cancels, right? This and that cancels. So what we have left is this. Limit of n approaching infinity of, and 64 and 6 cancel, so we have 30. Let's bring that outside. So we have 32 over 3. Good. Between the 6 and 64. And then what I have is n plus 1, 2n plus 1 over 3. Oh, not 3. N squared, right? Oh, we're almost there. So all we have to do is evaluate that limit, eh? Should we multiply it out? There are other clever ways to do it, but straightforward way is multiply it out. So we have limit of n approaching infinity of, is that 2n squared plus 3n plus 1 over n squared? You guys know how to evaluate that limit? And do you know the answer is 2, or you want me to show you? You want me to show you how to do this? Okay, so that gives you 2. So our answer is 64 over 3, which I believe is 21 and 1/3. Oh my God. That's a lot of work.